I'll be talking about Bloom filters today and how they are used in Dgraph per se. But like, let's first go into details as to what Bloom filters are, right? So yeah, okay. Uh, what are Bloom filters? So Bloom filter essentially is a probabilistic data structure, which means that the result of your query using this filter is not deterministic. So I mean, for each query, you cannot say, for instance, whether it's correct or not. We'll see, right? And for what kind of queries is it used? So it's used for queries like, does X belong in set S? So it gives you a yes and no. And in some cases, you can trust that answer. In other cases, you cannot. Yeah. So an obvious question is that why don't we use hash maps? Because they also kind of work for exactly the similar queries, right? The set belonging. So here
Anurag,
is, yeah.
I have a question. So why do we use it like if it is not reliable?
Yeah, we'll see. I mean, there are some
Okay.
cases where you are okay with having false positives, uh,
Okay.
so that you can save on space. So yeah, so hash maps can also give you queries results in order 1, but it uses like order n for the space. So as many keys you insert, your hash map size increases linearly, right? So where Bloom filters come on top is that they can work with a constant space. It need not necessarily always increase with the size of your set. So, but as a trade-off, they can give you false positives when checking for existence of X in set S. So what that means, that when a Bloom filter tells you that X doesn't belong to S, then you can trust it. But if it tells you that X belongs to S, then it might or might not belong. So we'll just see why that happens, right? So how would you go about implementing Bloom filter? So very simple. You'll build on top of what hash map already is, right? So Bloom filters work similar to hash map, but the key difference is you do not store the hashes of each entry separately, and you allow for collision. So let's go with an example. Suppose this is my total sample space. Anurag, Ashish, Michael, Manish, Aman, Zeni, and Tejas, right? And suppose I only allocate a hash map of size 4, and my hash function is such that it only cares about the first letter. So Anurag, Ashish, and Aman all are mapped to 0, Michael and Manish mapped to 1, Tejas mapped to 2, and Zeni mapped to 3. So suppose if I add Anurag and Manish to the set S, my hash map will look something like this, right? So now, as it might be evident, you can check, you can directly tell whether Zeni and Tejas are definitely not in the set by just order 1 lookup. But if you check for Michael or Manish, it's non-deterministic because both of them had a key collision, and you are not sure whether whether Manish is in the set or Michael is in the set. So that is where the non-determinism comes here, right? So yeah, so this is a very simple bare bone implementation of Bloom filters, right? Yeah. So now there are some obvious questions to think about when you know how Bloom filters are implemented. So in our implementation, what scope for improvement could you see? So you see here, the only thing driving the false positive is key collision, right? So if you could somehow reduce the key collision, then that would be an improvement, right? So that is like one obvious thing which comes to our mind, that collision should be minimized. Second is, can we handle deletion of an element from the set? So the thing is that you added few elements and you filled up your Bloom filter, but now you want to delete an element from the set. Is there a way to modify a Bloom filter? Well, not easily. You'll have to have like another separate data structure to maintain, because one particular key can correspond to multiple elements, like we saw in the collision. So Bloom filters do not work well with when you want to handle deletion of the elements. Cool. Third question is, what kind of hash function would you use? So choosing an hash function is important, because that is what your results into how many collisions you have, etc. So an ideal hash function for Bloom filter would be like, it's very quick, because you're gonna use it all the time while inserting as well as for querying. So it should be quick, and then it should have like a fairly ideally a uniform distribution across all the sets, but that is not possible. So like a fairly uniform distribution, as uniform as you could get, right? And it should be quick. So a lot of like cryptographic hash functions like SHA-1, etc., do not like really fit well here. Yeah. And then fourth question is, does using multiple hash function make sense? So now you might question that where does that come from? So that comes from when you wanted to minimize the collision. So suppose what happens is, think of it like this. Suppose you are using two hash functions for each key that you are inserting, and then whatever that hash function returns the bit, you are setting that to 1. So suppose your table hash map is kind of like half full. For it to return positive right now, there would be like a 50% chance. So it could return positive because it's like half full. But suppose you were querying it uh, suppose you were querying it for a key which you passed through two hash function, then it would for it to return true, it would have to be 1 for each of the slot which you got. So that means like 0.5 into 0.5, so your false positive goes down to 0.25 directly. Let's see with a demo how that works. So yeah, so this should go to, yeah. So when I'm saying like two hash functions, consider this. So you have this bit vector, and these are the two hash functions which you are using. So suppose I add few keys here. So it gave me 13 and 6, and those got colored here, right? Then I add few more. So now we have these four items in the hash map, and these are by using two hash functions, we got these keys colored. So now for us to check presence of any key, both of these hash functions should be 1. So that is why how you get down your chance for collision. So you see, right now it's giving 30 for Anurag. It's giving 13 and 6. So because we inserted that, but then is the element in the set is it's maybe because we are not sure. But for Anurag, it's definitely not in the set because not both the keys are set. Only one of them. So so even though 11 was set, but since you are using two functions, both of them had to be set. So you kind of decreased the false positive here. So and yeah, so that is why you can use multiple hash functions. So now you might be thinking that on one hand you want to like reduce the false positive, which means you want to reduce the collisions. But if you increase the number of hash functions, you will be filling up this table sooner, right? So that is true, and like that is why the false positive rate is not like directly dependent on the number of hash functions you like. It's not linearly dependent. There's like an optimum number of hash functions which you can use. So maybe let's talk about that. Yeah, so what does our like false positive rate depend on? So false positive rate depends on the number of elements we put in n in the set n, the size of our hash map m, and the number of hash functions which we use k. So if you have these n elements and you use these k hash functions, and suppose this is your m sized bit vector, so using these three, we can calculate our false positive rate. So finding the probability that an element returns false positive. So just like basic probability, if you see, so probability a bit is not set to 0 by one hash function is 1 minus 1 by m. So we are assuming that our hash function has a uniform distribution in this m size. So for it to set something to 1, the probability is 1 by m, and for it to set it to 0 is 1 minus 1 by m. Now a bit is not set to 0 by k hash function, becomes 1 minus 1 by m to the power k. And then the probability that it's not set to 0 by k hash functions after inserting n elements becomes this, right? Now, finally, the probability that Bloom filter return finally, the probability that Bloom filters return positive is equal to probability that all k bits are set to 1, which is equal to 1 like 1 minus this thing, right? And this is roughly equals to 1 minus e raised to the power k n by n. So you could see here that as your n increases, your probability of false positive increases. As your m increases, your probability for false positive decreases. And with k, it's you can find a optimum value of k in terms of n and n, right? So that is like the false positive rate for your Bloom filters, right? Then where do we use Bloom filters in Dgraph? So now you know that Bloom filters are useful when you are okay with few false positives and you want to save space in terms of instead of using like hash maps, right? So one particular use case is that suppose you want to find a key in your database, which is like stored in a Badger inside like some tablets. So first, what you do, since your tablets are like sorted, you do a binary search on set of tablets to narrow down the tablets we need to consider to iterate on to finding that key, right? Now, once you have those set of tablets, what you do that each tablet has an associated Bloom filter on it as well, and you check whether that key is present in that tablet or not. So if it's no, then you need not iterate over that tablet and you can just skip it. And if it says yes, then since it's a maybe, you have to actually iterate. So you could like again like iterate over fewer tablets using like Bloom filters, and that's why that's how you use Bloom filter basically in Dgraph. Yeah. Yeah, no, I mean that is like kind of the main place where we use Bloom filters in Dgraph. Yeah. So
Nice one.
yeah, anyone has any questions, comments?
Yeah, so do we like use the like vanilla version of Bloom filter, like because there are some thing like XOR filters and cuckoo filters that are like faster than Bloom filter and they take much smaller space than Bloom filter. So do we just use the Bloom filter, or do we have some like optimized version of that?
No, I think we directly use, so Bloom filter which we use in Dgraph is not like implemented by R. We directly use some library for using that Bloom filter. So yeah, we just use Bloom filter, and we store, so for each tablet we store the Bloom filter in the tablet itself. So each tablet has a like a associated Bloom filter which you can use to check the whether the key belongs in that tablet or not.
Arijit, we did try with a bunch of filters with different filters. We recently tried with roaring bitmaps and stuff. We tried with, I think, XOR filter as well. So each of these filters has its own property, right? The XOR filter does not let you, I think, mutate data, and I think it was using some different amount of disk space. So we decided to stick with Bloom filters. The Bloom filters we use is the general implementation of Bloom filter, but we have changed the hashing functions. So we wanted the Bloom filter to be fast. So we use this hashing function, which is a Go routine specifics. So, and this one is very fast. I don't remember its name exactly. It's in the Ristrato/Z package. You could look over there, but this hashing function is much faster than what you would use a normal one. Ashish did that change, so we changed that hashing function, and the Bloom filter package is a normal one. It's called Andrea's Bloom/Bloom package.
I think yeah, the main two configurable items whenever using Bloom filter is like which hash function which you want to use and like how much of a bit vector long you could want to like allocate.
Yeah, so just a question, like why didn't the XOR filter work out? Because like what I know is like we are mostly like storing immutable things, right? Like the levels are mostly immutable, and XOR filter works faster for like if you have a Bloom filter, it will work slower. So why didn't it work out in our case?
Yes, that's correct. One reason was the performance benefit is only, I don't remember exact benchmarks, but I can point to the PR. I have all the things mentioned over there. So XOR filter would work better only in one case. So you have two cases, right? Either your Bloom filter gives you a true value, as in it knows about the value, or it gives you a false value. So the XOR filter works better only in one of those cases. I don't remember which one was it, but it works only in one of those cases. That's one thing.
I think
Second, if we were to change the Bloom filter, right, the on-disk data format changes. Right now using Bloom filter, if you switch over to XOR filter, that the existing data is no longer compatible, and that means it's a breaking change. So for Badger who's using Bloom filter, this becomes a very major change, and we wouldn't do major change unless there is a significant benefit of doing that. XOR filter would give you a benefit, but again, that benefit is not significant when you're doing a query because it would go in the background to find the table. So a lot of things are involved, right? So the gain by switching the filter is not that much when you do a query. So that's why we decided to not use it, and it's a breaking change. So we did not do that.
Is the algorithm used and stuff like that also stored in the tablet as well, so that if in the future we do decide to change the algorithm or something like that, or the hashing function, then it'll be forwards compatible?
I think
no,
when you store Bloom filter in the tablet, that means that you store both the calculated actually you just store the calculated bit vector, and the library which you use from Bloom filter has the hashing function inside. So that remains same over the tablets. Only the bit vector for that tablet changes. Correct, Ibrahim?
Yeah, I have a correction to make. Tablets are different from tables. A tablet is something which Zero knows about. So Zero does resharding and stuff, right? So when it moves predicate, the container is called as a tablet. What we are talking about in this context is a table, is a Badger SST table. So let's not call it tablets. It's just confusing.
Yeah, sorry.
Second
SST
thing,
tables,
to answer Tejas's question, Tejas, we just store the Bloom filter. We don't store any meta information. Bloom filter is just a int slice, I think, int slice or a uint slice something. So we just store that. It's a struct, we marshal it and put it there. We have no meta. So even if we were to switch Bloom filter library, our Bloom filter would not work. It's just specific to the library we are using.
No, you could potentially change just the library hash function, and then
the hashing function would change, right? If you were to switch library, we use a custom hashing function, right? So if you were to switch to library B, it would use a different hashing function, and then your bits wouldn't match.
I see.
I have a question. Bloom filter does not store the count at particular index, like how many elements, how many keys did hashed up there. Okay. So when we delete the data, so like after some time, Bloom filter would all be set to 1, and that would be of no use.
So that is what, so it doesn't handle deletion of the data. So what you could potentially do is that you populate your bit vectors again in the background after like some time. So that way your tables are like kind of in a refresh state.
Badger tables are immutable. So what happens is once you flush something to the disk, it is never rewritten. We will read from it 100 times, but we would never rewrite it. So a Bloom filter, once it is written, would never be modified. Let's say you modify some key, so it would go into a different table, and the table you are currently looking at would eventually be discarded. So the Bloom filter will get deleted, the file will get deleted. So we don't have to deal with modification. We'll just create once and read it. So your problem with deleting does not occur. Like there'll be a new table which has a new Bloom filter. So that problem does not exist.
Ibrahim, just trying to understand that correctly. So when we do a delete, for example, basically what happens is you store a whole new set of data, like everything gets rewritten, and so the Bloom filter is getting rewritten as well. That's what you meant?
Yes, that's correct. For Badger, delete is a logical delete, right? So we would reinsert the same data, but marking it as deleted. So it would go into a new table, it would get a new Bloom filter, everything would be new. So you don't have to modify anything that's already there.
Cool.
I actually have a question which is maybe outside of the scope of this, but anyway, I just wanted to leave it there. So I'm assuming that when you open up a file that Badger has written to, the Bloom filter is probably at the start, and then the data sort of goes after that. How do you check that file is still maintaining its integrity? That is that there could be some case where you wrote the first bit of the file, you wrote the Bloom filter out, you wrote half the keys, and then your process crashed. So how do you sort of maintain that integrity?
So for a SST file, the Bloom filter is at the end, and it also has a checksum. But you need to remember how these files are created, right? We do not, so every time you insert a key, let's say you inserted foo, this file won't be created. So foo goes into an in-memory data structure, and this in-memory data structure will be flushed to disk all at once. So you would build an entire table all at once. But let's say your process got killed while you were flushing that table, right? So when Badger starts up again, it will see that there is an extra file, or maybe half written file. It would just ignore it because there's a manifest file which tells us that this is a file which was completely written and is valid. And when you start back up, you have lost half the data, right? Because your file was corrupted. So what would happen is the value log, the vlog file knows the head, has a head pointer. The head pointer tells you up until which point the data is correct, as in the data in SST is correct. So from the head pointer, you start replaying, and the half build data will be rebuilded into a complete new SST file. So you would lose the half data, but again, since your vlog file, you would reinsert back into the DB, it would get flushed down the levels, and now you'd have a complete new SS table file, and the old one would get removed from the system eventually.
Got it. Thank you.
Ibrahim, if we don't delete any data from Badger,
so if half thing gets corrupted, go ahead, Neeraj.
Yeah, I was saying like if we never delete data from Badger, so the hard disk keeps getting like occupied more and more. Like the size never decreases. Is it so?
I think that's where you run garbage collections, right? And
yeah, I
clean.
think like we should have a talk on LSM tree. That would.
Yeah. I think this is like
so
a
it's
good
like,
precursor.
Yeah.
I have two doubts related to this also. So when we use the XOR, so it can be so. Let's say we had two keys that were mapping to number 13. So when we XOR it twice, then it will become 0, right? And it will say, okay, this key doesn't exist at all. So like, how can we use a XOR?
No,
You would not XOR it, right? You would
you're
just
not
set the
XORing.
bit.
You are just setting the bit, right?
Yeah.
Oh, okay. We'll just set it. Cool. And one more, like instead of just updating only one array, so let's say we have size 100 array, and we have 10 functions, and we are just updating those 10 hash functions into this 100 size array. Instead, we can like create 10 different arrays and like map differently. So like, will that be more efficient or something?
No, it's same thing, right?
No.
I mean, you're just breaking that 100 into 10 chunks. At the end, it's the same, right?
100 into 10, but every hash function will have value from 1 to 10 actually. But right now, every hash function has value 1 to 100. So I don't know, like I don't think we can even compare those times. There will be too much of math.
I think he is asking key instead of using two hash functions, would it be better to use two Bloom filters?
Two smaller Bloom filters, right? Yeah. I think this answers, I mean, depends on like what you want for your hash functions in the Bloom filter is to be like independent. So if you could like make them independent, then both of them having one with a sample range of 1 to 100 versus like one having range from 1 to 10. I'll have to like check basically which one performs better asymptotically. But the function, like the hash functions which you choose have like ideally should be like independent from each other.
I'm guessing the logic over there is that the only reason you want to have multiple Bloom filters is if your table size would be different from each algorithm. But compared to that, if you looked at it, you're just putting one bit in each place, saying either presence or not. So I'm guessing the idea over there is that it's easier to run, say, 5 algorithms and use up all the bits rather than leaving one bit and then just leaving the rest of that byte empty.
Also, you would always want to have less Bloom or less hash functions because the goal is to have a probabilistic data structure, right? If you want accurate things, you just use a map. But the goal here is to reduce the size and try to get a data structure which will tell you if this exists or not. And the no answer is always like the correct one. If it says that it does not exist, that means it does not exist. In Badger, we have this Bloom filter false positive rate. Depending on what percentage is set over there, your size of Bloom filter will vary. So by default, it's at 1%. that's what we set it to. If you set it to 10%, let's say, then your size of Bloom filter will decrease, right? Because you have given it more room for error. So it just depends on how much your disk versus how much accuracy do you want. So that's the goal behind using less hash functions as well.
Which actually brings me to, if in that formula for calculating the accuracy, what are those values for, by default for Badger? What's the size of the table? How many hashing functions do we run?
So we do 2 hash functions. I think that's common for Bloom. For most of the Bloom filters, we do 2 hashing functions, and we have 1% false positive rate, and the Bloom filter we get is about 5 MB in size. For about 64 MB of data, we get about 5 MB of Bloom filter, which mostly consists of keys.
Got it. Thanks.
Yeah, I guess that's all I had from my end. And thanks, Ibrahim, for chipping in. Does anyone else has like any more questions? We are right about on time.